Welcome, my name is Dr. DrWedding, and this is DrWedding, DC18. Kirchhoff's current law. In this video, you will learn what Kirchhoff's current law is and how to use it. Kirchhoff's current law is covered early in this series because it is easy to understand when it is demonstrated on a very simple circuit. This video is only designed to teach you what Kirchhoff's current law is, along with some basic examples. More advanced applications will be covered in later videos. If you are trying to learn nodal analysis to solve series parallel circuits with multiple power supplies, then this is not the correct video. Nodal analysis is covered in detail in a later video. Even if your goal is to learn nodal analysis, you should watch this quick video. Without a firm understanding of Kirchhoff's current law, you will not be able to correctly create the equations that are used to solve a circuit with multiple power supplies. Kirchhoff's current law is shown below. It may look intimidating, but it is very easy to understand and use. The sigma in the equation means you take the sum of a list. The list that you are summing up is a list of currents. Because each time you use this equation, the number of currents in the list will be different, the current has an index, k. K goes from 1 to the end of the list. The end is represented by the letter N. The currents being summed up are meeting at a junction point of 3 or more wires. This junction point is called a node. The currents entering the node are positive and the currents exiting the node are negative. And the sum of all these currents will be equal to 0. So, Kirchhoff's current law states, the sum of the currents at a node is equal to 0. This will quickly become obvious when you see an example. Furthermore, the math behind it is so trivial, a 7th grader could use this equation to find a missing current. The concept of Kirchhoff's current law is very easy to understand. Pretend you have a garden hose. And on the end of the hose you add 3 small tubes that will be used to water 3 different plants. If you applied Kirchhoff's current law to the hose, it would say that the amount of water entering the hose plus the water exiting the hose will sum to 0. So if there is positive 3 gallons per minute entering the hose, then there must be negative 3 gallons per minute exiting the hose. And the sum of the inputs and outputs will equal 0. Let's apply this law to a parallel circuit that we have solved in a previous video, because we already know all of the currents and voltages for this circuit. Example 1. Verify Kirchhoff's current law at the highlighted node. Start with the equation for Kirchhoff's current law. We know the 2 red currents. They are the currents through R3 and R4. We can use these 2 red currents to find the blue current. The blue current is the current that is feeding the node. To use Kirchhoff's current law, we add up these 3 currents, where the currents entering the node are positive and the currents exiting the node are negative. To make this equation equal to 0, the unknown current is positive 15.5 milliamps. Because this current is positive, it is entering the node. Here is another example. Example 2. Verify Kirchhoff's current law at the highlighted node. As before, start with the equation for Kirchhoff's current law. We know the 3 red currents. They are the currents through R2, R3, and R4. We can use these 3 red currents to find the green current. The green current is the current that is feeding the node. To use Kirchhoff's current law, we add up these 4 currents, where the currents entering the node are positive and the currents exiting the node are negative. To make this equation equal to 0, the unknown current is positive 23.5 milliamps. Because this current is positive, it is entering the node. Here is the final example. Example 3. Verify Kirchhoff's current law at the highlighted node. As before, start with the equation for Kirchhoff's current law. We know the 4 red currents. They are the currents through R1, R2, R3, and R4. We can use these 4 red currents to find the orange current. The orange current is the current that is feeding the node. To use Kirchhoff's current law, we add up these 5 currents, where the currents entering the node are positive and the currents exiting the node are negative. To make this equation equal to 0, the unknown current is positive 29.5 milliamps. Because this current is positive, it is entering the node. These 3 currents have been added to the circuit. Using Kirchhoff's current law, you can see that the current is not the same in the upper wire because the current is broken apart at each node. When all of the currents are added to the circuit, you can see that Kirchhoff's current law also holds for the lower nodes. The only difference is the red currents are now positive because they are entering the nodes, and the blue, green, and orange currents are negative because they will be exiting the nodes. I hope this video has helped you understand Kirchhoff's current law and how it is used to find a missing current. At this point, the math is trivial and you may not see a good use for it. But as the circuits become more complex, both Kirchhoff's current law and Kirchhoff's voltage law will become very useful. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.